Hi, I'm Anay Mehrotra. I'll be talking about our paper titled Fairness for AUC via Feature Augmentation. This is joint work with Hortense, Fong, Vineet, Kumar, and Nisheeth Vishnoi at Yale University. Recent work has shown that traditional classification methods can have disparate performance across protected groups such as people of a specific race or gender. This leads to real-world adverse impact where, for instance, people of color were denied mortgages and bails at significantly higher rate than people with lighter skin tones. This has led to rich research in developing solutions for fair classification. However, the real world deployment of these solutions still faces challenges, and one major challenge is that they assume the training data is sufficiently predictive for all protected groups. This may not be true if data is collected to optimize predictivity for the majority group. A recent survey of practitioners also found that most of their interviewees seek guidance at the data collection phase rather than the model development or training phases. The question here is that which data should one acquire to ensure that the classifiers trained on this data are fair? Before considering potential approaches, let's look at a model of data. There are n acquired training samples, where each sample contains a class label y to be predicted, a protected attribute a, and a feature vector x with d features. All of this data has already been bought or collected by a manager. In addition, there are m-d auxiliary features, which the data manager can buy through data brokers. We'll focus on classifiers formed by thresholding generalized linear models and later consider their extensions to other classifiers. For a classifier F, we measure its predictive performance using AUC, that is the area under the receiver operator curve of F. AUC is used in binary classification tasks when both type 1 and type 2 errors are important. There are several benefits to using AUC over accuracy. First, AUC is invariant of the threshold used for classification, which is useful if the acquired data would be used by different teams that use different thresholds to achieve a desired trade-off between type 1 and type 2 errors. AUC is also robust to imbalance in the sizes of positive and negative classes. This is particularly useful if the class sizes can vary across time or across teams. We measure the bias of F using a metric based on AUC. The bias metric measures 1 minus the ratio of the minimum AUC of F across protected groups to the maximum AUC of F across groups. Intuitively, this is close to 0 if F has a similar AUC for each group, and it's close to 1 if the AUC of F varies significantly across protected groups. The challenge in deciding which features to acquire is that before purchasing these features, the manager only has access to the first few moments of the features from the data broker. We study this problem under the binormal framework of data, where conditioned on the class label and the protected attributes, all features are drawn from a multivariate normal distribution. Under the binormal framework, the AUC of the best generalized linear model has a closed form expression in terms of the first and second moments of the features. This expression has been observed to be robust to deviations from the binormal framework. The benefit of having this expression is that the data manager can use it to estimate the resulting AUC before acquiring the features. Our first observation is that during exploratory phases, several existing works use the unconditional distributions of features to identify which features they'll use. However, classifiers trained on features with the same unconditional distribution but different class conditional distributions can have very different AUCs. Hence, we'll use class conditional statistics of features in our approach. Still, there are many approaches to decide which features to acquire. For instance, a natural approach is to acquire features that minimize the bias according to the expression of the AUC above. However, to minimize bias, this approach can select noisy features that have low predictivity, leading to a lower overall AUC. Another approach is to select features that most improve the overall AUC, hoping that this increases the AUC for all groups. However, when features are more predictive for one group compared to others, this approach can result in classifiers that have a high bias. The question is, which features should you, as a data manager, select in order to ensure that the output classifiers have both a high AUC and a low bias? Our approach is to select features iteratively. At each iteration, we first identify the group with the minimum AUC and then select the feature which most increases the AUC of this group. We call this procedure FairAUC. FairAUC seeks to increase the AUC of the group with the minimum AUC rather than explicitly minimizing the bias. This is because minimizing the bias may select noisy features which while equalize the AUC across groups, do not increase the AUC of any group significantly. Moreover, because FairAUC uses the expression of AUC under the binormal framework, it only needs access to summary statistics of the data and specifically their first and second moments. Theoretically, we show that in each iteration, this procedure strictly increases the AUC of the lowest AUC group and give a lower bound on the amount of increase in terms of the first two moments of the data. Moreover, we show that at any iteration, FairAUC does not decrease the AUC of any other group. This shows that over multiple iterations, FairAUCs will select features that increase the AUC of the lowest AUC group significantly. And if at any iteration, the lowest AUC group changes, then in subsequent iterations, FairAUC would select features that maximize the AUC for the new lowest AUC group. To gain some intuition, consider an example with two protected groups, a majority group A and a minority group B, with three types of features. The first type of features favor group A. They increase the AUC of group A by 20% and only increase the AUC of group B by 5%. The second type of features favor group B. They improve the AUC of group B by 20%, but only increase the AUC of group A by 5%. The rest of the features are noisy. They don't improve the AUC of any group at all. Here we compare the performance of FairAUC to two other iterative procedures, max AUC, which at each iteration selects a feature that maximizes the overall AUC, and min bias, that at each iteration selects a feature that minimizes the bias. Initially, the set of acquired features are more predictive for the majority group, which is group A. Hence, the trained classifiers have a higher AUC of 30% for group A and a lower AUC of only 10% for group B. Because of this, in the first iteration, FairAUC selects a feature that favors group B. After two iterations, the AUC of group B becomes higher than that of group A. So now FairAUC selects a feature that favors group A. And this goes on. At the end of four iterations, the AUCs of the two groups are 65% and 75% respectively, and the resulting bias is 0.07. In comparison, in each iteration, max AUC selects features that favor group A. This is because A is the majority group, and because of this, increasing the AUC of group A by a certain amount has a larger effect on the overall AUC than increasing the AUC of group B by the same amount. At the end of four iterations, with the features selected by max AUC, the bias is 0.7, which is much higher than the bias of FairAUC. And the AUCs of the two groups are 100% and 30%, which, depending on the relative size of group A, can be either higher or better or worse than the AUCs with FairAUC. Min bias, on the other hand, starts by collecting a feature in the first iteration that favors group B. After the first iteration, the bias is 0.14. And in all subsequent iterations, min bias only selects noisy features. This is because selecting any other feature would have increased the bias at that particular iteration. At the end of four iterations, the resulting bias is still 0.14, which is worse than that of FairAUC. And the AUCs of the two groups are 35% and 30%, which are also worse than those with FairAUC. In terms of applicability, FairAUC can also be used as a heuristic with classifiers beyond generalized linear models. In this case, FairAUC does not need access to the internal details of the classifiers, but only requires access to the input features and the output confidence scores. To see a concrete example of how FairAUC may be used in practice, consider a bank that would like to automate parts of its loan decision-making pipeline by predicting whether the applicants would repay the loan. The bank already has access to some features of its loan applicants, such as their current income, age, property type, and past education. It can use these features to predict whether an individual would repay the loan or not to certain accuracy. However, it can also go ahead and acquire additional features about its applicants, such as their credit score and their spending history from data brokers. Here, if I'm a data manager at the bank, I can decide an acceptable level of bias epsilon. And then, if the bias of the trained classifiers is higher than epsilon, I'll go ahead and acquire additional auxiliary features. To do so, I'll first request summary statistics of auxiliary features from data brokers. Then I'll use FairAUC with these summary statistics for one or more iterations to decide which features to purchase and then purchase these features. Finally, I'll take all the data gathered so far and train a new classifier using this data, and then repeat the process if needed. Empirically, we evaluate FairAUC on both synthetic datasets and the composed dataset. The synthetic dataset we use follows the binormal framework. It has 50 features, where half of the features are informative for at least one group, and the other half features are uninformative noise. On Compass, we consider two protected groups, individuals whose age is at most 25 and individuals whose age is above 25 years old. On both datasets, we find that FairAUC decreases bias and improves the overall AUC. In comparison, MaxAUC has a higher bias and a similar AUC as FairAUC, and the other baselines have a much lower overall AUC and a similar bias as FairAUC. To conclude, we propose a feature augmentation approach that intervenes at the data collection phase to help improve the fairness with respect to AUC. It acquires features iteratively, and at each iteration acquires the feature that most improves the AUC for the disadvantaged group. The procedure can incorporate any threshold-based classifiers, and we give theoretical results with classifiers derived from generalized linear models. Empirically, we observe that FairAUC equalizes the AUC between protected groups at a small cost to overall AUC. There are some directions to improve our work. Since our procedure considers AUC as the performance metric, it's not applicable in contexts where AUC is not suitable. Our procedure also assumes that the underlying features are approximately binormal, and large deviations from binormality can undermine its effectiveness. Finally, it's also important to consider FairAUC as part of a broader system for mitigating bias, in particular one which combines pre-processing, in-processing, and post-processing algorithm approaches with FairAUC.